All right, we're gonna start. I think everybody is busy at CSU GBM. There's like free sushi or whatever. So I'm hoping that's why there's not that many people here, but we'll see. So I know you guys all signed in, but I guess Rohan also signed in. Today is going to be ML Monday lecture number 6. We're going to be lecturing on training neural networks. So introductions. I'm sure most of you guys know me, but my name is Alvin Wong. I'm the education lead of GatorAI. And there's also other ML lecturers who do some of the other lectures, but unfortunately they could not make it today. That's Kartik, Siobhan, and Srinikath. All right. So review of the previous lecture. Was there anybody who was here out of the 5 of you that was here? Last lecture you got Rohan, Carson, and you get to, you were here, and you're not here, and you were not here? All right. Does anybody want to give like a brief overview of what happened last lecture? Any of you guys? I'm going to try and make this as interactive as possible so it's not boring for you guys. Anybody?
I mean, it was feed-forward neural networks, is that what it was, right? Yeah.
Yes, feed-forward neural networks. You want to explain a bit more about that?
I'll try my best. They're the backbone of deep learning, apparently.
Backbone of deep learning, nice.
And we learned about like forward pass for computing predictions.
Yes, all right.
And backpropagation, which computes the gradients, which I don't exactly remember what it was. But
That's good. Anybody else? Rohan? No? All right, yeah. Yeah, that's good. So what we learned about last week was, like you said, backpropagation, gradient descent. So really how the neural network kind of learns these weights and parameters so that it can kind of fit the functions that it needs to, right? So we're going to go over a little bit about that. So recall a neural network. So a neural network is essentially a group of neurons, each grouped together into a layer. So each single individual unit is named a neuron, and each neuron belongs to one layer. And each layer is what we say fully connected to both its previous and next layer. And you can kind of see a diagram of a general neural network. So the first layer is the input layer, which takes in the inputs. These are usually your features or some other type of values that you might put into it. We have the connections, and then the middle layers are called the hidden layers. These compute essentially what are called latent features. So these are features in the latent space that the neural network might pick up on. And usually these latent features are a combination of multiple features, and they're very hard to kind of discern what they actually are. So this kind of plays into the idea that a neural network is kind of a black box, right? You can't really tell what kind of information is being passed through these hidden layers. All you kind of really know is that backpropagation and gradient descent somehow makes it work. And at the output layer, when you get out your output, you get pretty decent results some of the time. So that's kind of what's happening here. Question?
Wait, can you make sure that the slides are on the screen?
Is it not? It's not working?
No.
Let me check. Let me double check that.
Just edit the display capture.
I thought it's.
Put the display capture.
Where is display capture, bro?
It's a logo where you're clicking. Yeah, edit that. There you go.
Why was it not working? That's great. All right. Okay. Well, for people who cannot see before, neural network, review previous lecture. That's all we did so far. So neurons, right? So we'll move on to neurons. This is the single unit of computation, like I said, in a neural network. It's given by the function you can see right there. And essentially what it does is it takes the dot product of the weights and the previous inputs that it gets. It adds a bias term, and then it uses the activation function, which is the function denoted by f, and produces its output. And you can see with the chart on the right kind of the flow of inputs, right? So you take all of the inputs that you're given, you multiply it by its weights, you get a linear combination, you add your bias, and then you get z. You plug z into your activation function, and you get your final output y for the output of the neuron, right? And so in a neural network, you have multiple of these neurons all acting together, and that's kind of what you get, right? And remember that w dot x is the dot product operation here, right? And so w and x are vectors, right, which are respectively vectors of the weights and vectors of the inputs that you are giving into your neuron. And there you can see kind of the what the dot product actually represents, which is just the summation of the products of xi, wi, going from 1 to n, right? And so we can really take anything to be kind of our activation function in this case, but in most cases, what we want our activation function to be is actually ReLU, which is a specific kind of non-linear activation function. So we could use the identity function as our activation function. We could use sigmoid as our activation function, but usually we use ReLU or something that is at least non-linear. We kind of talked a little bit about last week why we want to use non-linear activation functions. Does anybody want to explain why you would want to use non-linear activation functions? Anybody? Yes.
I think it was like because otherwise it'd just be like linear.
Exactly. Yeah. So essentially, what's happening here, right, is we're taking in kind of a weighted sum, a linear combination of these non-linear activation functions, and this lets us approximate any kind of function given enough non-linear functions that we're using, right? So if you add a bunch of linear functions together, no matter what you do, you'll end up with a linear function, right? This is actually like kind of a proof that you would do in a linear algebra class. It's probably one of the more early on proofs that you'll do, proving that a sum of any type of linear functions will also be a linear function, right? And there's also this idea that neurons were loosely based on actual neurological neurons in the brain, right? There's a kind of a lot of contention around this. A lot of machine learning researchers now say it's not really true. And if you talk to neuroscientists, they say that's not really true. And the reason for this is because the first kind of neuron that was created was called the perceptron, right? So it was a neuron that had no bias term, and it had a step activation function, which essentially meant that it would only send the output, y, right, if the z was above a certain threshold, right? So maybe, for example, it was above 1, it was above 2, or something like that. And that was kind of based on the idea that neurological neurons in the brain, they only fire once they hit a certain potential threshold. But we kind of learned like a lot later on, or not a lot later on, we actually learned pretty early on that's not really how brain neurons work. It's not just firing all at once or not at all. There's information in between kind of really. So not only was the machine learning neuron not really based on a good example of neurological neurons, but it's also very flawed in that regard. Right, and the perceptron was created by a guy called Frank Rosenblatt, and this was like created in the 1900s, so it was a while ago, to be honest. All right, so activation and loss functions, right? So we talked a little bit about activations before, what kind of activation functions you can use. So like I said, ReLU is kind of the main activation function that is used a lot. There's other activation functions that you can use, but usually these activation functions are used at the output layer of a neural network to kind of map your inputs to a proper output range that you want, right? So sigmoid, you can see, kind of restricts the output values from 0 to 1, right? Tan-H, we have softmax and stuff like that map them to different things. Softmax is used for multi-class classification, right? So softmax maps values to a probability density function, right, across multiple classes that you can use. So that's really great for obviously multi-class classification. So a good idea here is that we want our loss function to match our activation function, right? So say, for example, at our output layer, we were trying to use, we were doing multi-class classification, right? So okay, sorry, my bad. On the example on the slide, let's say we have a regression task and we're using mean squared error as our loss and tan-H as our activation function. This would be a mismatch because tan-H, as you can see, is limited from the values of -1 to 1. So unless your regression values are actually from the values or the range of -1 to 1, it's kind of a mismatch. You want something like maybe a linear activation function or something of that regard for your regression function. In the similar notion, if you had multi-class classification, you wouldn't want to use something like ReLU or linear as your activation function for your output layer. It just really wouldn't make sense. So you also want to match your loss function to that to make sure that your training goes properly, right? So we'll go back to propagation and gradient descent. So I kind of have two GIFs here. I like the animations. I think they do a good job. I think together they kind of come together. I think both of them are missing some key elements. So let's look at the top right one first. It kind of shows how as the inputs go through, you make your forward pass, right? You're storing the predictions of your forward pass. And then once you get the output, you compute the loss from the loss function. And then you go back through the neural network with backpropagation using the chain rule to calculate the gradients. And then you take a step in the direction going downwards to, of course, decrease your loss. And then in the bottom right, it kind of shows how the gradient is kind of calculated. You kind of see all of these arrows. They're of different magnitudes and they're adding up, right? So from the output layer, let's say the second last layer, it has kind of a nudge in a direction for its weight and bias given by every single output neuron, right? So you can kind of see in the bottom right how every single output neuron is giving it a value or a kind of like a push in which direction it wants the neuron to go. That kind of shows how the weights are being updated by the layer in front of it. And this kind of goes through all the rest of the layers as it goes backwards, right? So the backpropagation, what it really is in layman terms, is a method to efficiently compute the loss gradients with respect to the parameters using the chain rule. This algorithm was developed by a guy called Geoffrey Hinton in 1986. And so this was kind of a big breakthrough at the time because nobody really knew how to train neural networks efficiently, especially deep neural networks. And this was kind of the research paper that kind of made it come all together. But actually at the start, a lot of people said that backpropagation, even though it worked, they said it was inefficient and it converged improperly. But even today, this is what we use for neural networks. So you can imagine from 1986, people were even saying back then, like, this is a bad method, you know, it doesn't work. Even Geoffrey Hinton, he said himself, like, if he could redo it, everything, he would start from scratch on how to train a neural network and not use backpropagation because he thought it was a bad idea. But it still works today and it's still used, so that's why we're teaching it. So the algorithm for backpropagation, right, is like we said before, we compute the forward pass and save the intermediate results of each neuron. We compute the loss. Once we reach the output layer, we compute the loss. And then from that loss on the output layer, we perform the backward pass using the loss. And then we go layer by layer and compute the gradients using chain rule. And then we update the weights based on the gradients given, right? And so backpropagation and gradient descent go hand in hand. So gradient descent, right, is just we're updating the parameters in the direction that reduces the loss using the computed gradients. And right, this is, like we said, computed from the layer ahead of it using backpropagation, right, which uses the chain rule. Is there anybody who has any questions? Just making sure. No? If you guys have any questions, yeah, just make sure, feel free to raise your hand and get to you as soon as I can. So the next thing I want to talk about is the universality of neural networks, right? Or also known as the universal approximation theorem, right? So the kind of neural networks we're talking about are called feed-forward neural networks, just as a reminder, right? So feed-forward neural networks really just means that we pass the information from the input layer to the output layer, and there's no loops or anything of that regard. So there's no like recurrent neural networks here right now. And essentially, even a simple feed-forward neural network can approximately represent any function because it has a weighted sum of nonlinear functions like we described before. And so this universal approximation theorem holds true if we're allowed to use any number of neurons in a single hidden layer. And it's also true if we assume that we can use any number of layers, each with a fixed number of neurons. And you can kind of see the GIF in the top right kind of shows, it uses a bunch of ReLU functions, right? And it actually transforms these ReLU functions to kind of approximate a polynomial function, we can see, right? So the blue line is kind of the approximation and the white lines are the ReLU functions it's adding. And intuitively how this makes sense, right, is if you guys remember from like probably high school math, if you have a function, you can like transform it, right? You can like move it to the right some, you can move it to the left some, you can vertically translate it, horizontally translate it, you know, like you can mirror it across the y-axis, mirror it across the x-axis. So the intuition here is that essentially neural networks, by using a weighted sum of nonlinear functions, right, it kind of transforms the nonlinear function across and then adds it to its function. And by doing so, it's kind of able to slowly approximate the function that it wants to have, right? That's kind of the intuition around here. So neural networks, the kind of architecture we want them to have is described usually as a funnel architecture. We want the network to look like a funnel. So what that means is we start at the input layer with a large number of neurons, and as we go further down the layers, layer by layer, we want to reduce the number of neurons we have. And the intuition for this, right, is that as we go down the layers, we want the neural network to learn more compact latent features, right, that represent more information in just a single weight, or a single value, right? And that helps the neural network learn the kind of most important features, right? That's kind of the intuition here. So for most tasks, you have a large number of input vectors and a small number of output vectors, right? So for example, for multi-class classification, let's say you have 100 inputs and you have 10 output classes, right? So let's say you have images that are 10 pixels by 10 pixels, right? So you have 100 pixel inputs and you're trying to classify them into 10 different categories of images, right? The number of latent neurons in each layer that you might have is you might have 100, and you might go down to 64, 32, 16, and then you go to 10 for your output layer, right? So that's the funnel architecture we're seeing here. And once again, we want our activation function and our loss function to match, right? So for example, we'd probably be using something like softmax on our output layer. We'd be using ReLU activations on every other layer, and we would be using cross entropy for our loss function, right? That's kind of what's going on here. And you can see on the bottom right kind of how the layer number of neurons decreases as you go through the layer width. All right, so hyperparameter tuning for neural networks. So recall that hyperparameters are parameters that are set before training, and they kind of define any configurable part of a model's learning process. And the most important part is they are not learnable from the data, even though they influence how the model performs, right? So one of the biggest problems with neural networks is that there are endless options for hyperparameter tuning, right? We can change so much stuff about them that kind of change how they work. We can change the number of neurons we have in each layer. We can change the number of layers, which activation functions we use, which loss function we use, kind of the connections between the layers. We can change the step size we're taking for gradient descent. We can change the batch size that we use, right? And there's just so much type of stuff. So one of the things that people like to talk about in terms of hyperparameter tuning is the idea of the no free lunch theorem. It's a theorem in machine learning research, which basically is that you can't train a model to perform universally well on every single task. A model that performs well on some task has to kind of sacrifice performance against another task. So you really don't know kind of if your model is going to perform well on a certain problem unless you build it and test it on real world data. So that's kind of the idea of the no free lunch theorem. So I would just say make sure when you're actually training your models to test it and see how it performs, right? So there are some general tips though for hyperparameter tuning for neural networks, right? So for the number of layers, a general rule of thumb, right, is you want to use a longer neural network rather than a shallow and wide one, right? Like we said, we want the neural network to kind of learn compact latent features that represent a lot of information, right? So that the neural network can kind of figure out what is the strongest features to use, right, in its predictions. For the number of neurons in each layer, right, we talked about this a lot, so we just want to use this funnel architecture for the number of neurons. And the idea also is that you want to make your layers wider than you need them to be, and then later you can regularize. This is also just a general idea, right? You want to make your model extremely complex first and kind of see if it's overfitting, if it's able to capture the true relationship. And then if you see that it's overfitting, you can kind of cut stuff off and make it less and less complex, and then it'll stop overfitting and you can kind of go from there, right? So some other general tips for hyperparameter tuning, right, is the learning rate. So the learning rate, does anybody recall what the learning rate was? We talked about it last week and also a little bit, I think I talked about it here. Yes, Carson.
Was it like how big of a step you're taking and changing your weights?
Exactly, right, yeah. So it's how big of a step are we taking once we calculate the gradient and we're taking the step in the opposite direction, right? So the learning rate is, a little bit odd to tune, right? Because the loss landscape kind of changes for every single different problem, right? So it's kind of difficult to say. So people have came up with these things called optimizers. And optimizers are kind of ways to dynamically change the learning rate depending on how the model is training and what the gradients are. But normally it lets you choose a starting learning rate. So we'll go from there. So normally you want to start with a really low learning rate. And then after each run, you want to see how well it's performing. And you kind of can multiply it by a factor of 10 after each run. You kind of monitor the training, and then you see if it diverges from the training that you've done before. And once your model starts diverging, then you say that you've gone too far in kind of making the learning rate too large. And the reason you kind of want to hit this threshold, right, is because if your learning rate is too small, often what happens is you get stuck in the local minimum or local minima or saddle points, right? And you kind of get stuck there, and you can't really find a better minimum for your loss function, which is not really what you want, right? So that's why we want to make the learning rate kind of the largest it can be, right? So different types of optimizers. You can see I have another GIF. I like GIFs. We have the GIF on the right-hand side that has different optimizers. So we have stochastic gradient descent. We have stochastic gradient descent with momentum, eta grad, RMS prop, and then we have atom optimizer. Generally, the most commonly used optimizer is atom or RMS prop. I can give a little bit of detail on the optimizers. They usually come with two main ideas, right? The first being momentum, right? So momentum is just essentially the idea that the optimizer will store the direction that that kind of you went in the previous batch, and you'll kind of use it to inform your next step, right? So for example, let's say you took one step in one direction, and the next step in the next direction goes a completely opposite direction. You're going to kind of average those out and see kind of where you're heading, because maybe you think that your batch that you're using is a very weird batch, right? So you don't want to take a step in a completely wrong direction. You want to use the previous batches to kind of help inform you of your direction, right? The next kind of standard idea with optimizers is called adaptive learning. So adaptive learning is kind of the idea that different parameters in the neural network will be changed at different rates. So essentially what we want in this instance, right, is atom or RMS prop or whatever optimizer you're using for adaptive learning. It will kind of change the parameters at different levels depending on how the gradient is, right? So for example, if you're taking lots of steps, if your optimizer has noticed you're taking lots of steps in very different directions, what it will actually do is it will decrease the learning step, right? Because it notices that you're kind of going all over the place. And so it'll lower it to kind of figure out if you can get in the right direction if you lower the learning rate, because it maybe thinks that you're jumping over a local minimum or something like that in your loss landscape, right? So that's kind of what it is for optimizers. And you can see on the GIF too that atom and RMS prop, they kind of navigate the loss landscape a lot better. They're able to find the minimum of the loss much faster. And it might seem like it's not that big of a difference on this graph, but when you're training extremely large models, right, like ChatGPT or something like this, you're saving really a lot of money on computation and time. So that's why people use kind of optimizers like this. It just really is really efficient, especially at higher levels when you're training big models. General tips for the batch size. So recall that the batch size is the largest amount of data that you pass through the model at one time to calculate your gradient. So normally for performance, there's two sides to this for what batch size you want to use for the data. For performance, you want to use a smaller batch size, and this is for speed, right? Because the smaller batch size you can have, where is this? I think I might have got this mixed up. Oh yeah, sorry. For performance, you use the smaller batch size, and that's because you kind of can take smaller steps and you can kind of see what's going on. And then for speed, you want to use the largest batch size that you can fit in your GPU VRAM, right? So it kind of makes sense, right, that GPUs are very good at parallel processing. So if you fit a large batch size in your GPU can perform the calculations much quicker than rather if you were to give it lots of small steps and it calculates them individually and you have to feed it even more data and stuff like that. So batch size, it really depends on what you're aiming for, either performance of your model or the speed that you want to train your model at. Question?
Yeah, sorry, what did you say batch size was again?
Batch size is essentially the size, like how many data points of your training set are you passing through the model at once to calculate the gradient, right? So kind of like to expand on that, so like stochastic gradient descent is you have a batch size of 1, so you would pass only one example through, and then you would calculate the gradient, right? But that can like be a bit noisy because maybe some of the data is not very clean, right? Stuff like that. So what a lot of people will do is they will batch data together. They'll all calculate the gradient for all of them, and they'll probably do something like averaging or stuff like that. So they get like a more what's considered to be like a better step direction, right? You want to go in there. So yeah. And then for the number of epochs, right? Epochs are a single epoch is essentially you're training the model one time on the entire data set, right? So the number of epochs you train, normally you want to use early stopping for training. So what that means, like let's say you train your model on the data set and you train it like 60 times on the same data set and you don't see any improvement in the validation accuracy, then you'll use early stopping. You might say you're early stopping after 10 epochs, right? If my validation accuracy doesn't improve, then I'll stop training the model, right? And stuff like that. So this is really good because not only does it prevent overuse of computational resources and also a lot of time, but also it prevents overfitting, right? Because eventually, if you train it for long enough, your training accuracy will increase, but maybe your validation accuracy will not increase. So if you just keep training it, hoping for a validation increase, eventually you'll find that your model actually overfits and that it'll probably perform even worse on unseen data than if you were to use early stopping and not actually prevent the overfitting, right? All right, so another issue with training neural networks, question?
Yeah, sorry, could you go over what overfitting was again?
Yeah, so overfitting is essentially when your model kind of, how should I put this? It kind of fits to the noise in the data, so it no longer captures the true relationship between the input information and the output information, right? And it kind of is just adhering to the noise. So it kind of memorizes the training data and is memorizing all of the information in there, but it's not capturing the true potential, right? So for example, if you have a picture of a data set of pictures of cats and dogs, right? And you're training a neural network to determine if a picture of a cat versus a dog, right? For humans, right, we're able to generalize well, and we might say like, oh, a very easy features, right, is that cats have, maybe shorter pointier ears, maybe dogs have longer flappier ears, right? Maybe cats have, shorter noses and dogs have longer noses, right? Those are kind of like very visible features that we can see, right? But the neural network would kind of forget about all of that and would just focus on very specific noise that it could use to figure out if the image was a cat versus a dog, right? And that noise might not be indicative of truly what makes a cat and what makes a dog, right? So it's kind of the idea of a model memorizing the training data rather than learning the true representation. Does that answer your question?
Yeah, so is it looking more towards like the outliers, is what you're saying? Like it's using outliers to mess up the general pattern of what the actual curve is saying, or?
I wouldn't say it's outliers. It's more like it's looking at patterns that don't really make sense, right? So they're kind of what we'd say like non-robust features. They're features that don't actually work in the real world, right? It's just relations it's managed to capture in the data. For example, let's say every single picture of a cat, there was a certain image artifact in the bottom left corner, right? And that the neural network was able to latch on to that image artifact and say, oh, every single cat image has this image artifact. Now I know if it has this image artifact, it's actually a cat, right? A human would never be able to see that and be like, okay, this is the reason why this image is a cat, stuff like that, right? So that's kind of what I mean by overfitting. Okay, vanishing and exploding gradients. So one of the issues with training neural networks is this problem of vanishing and exploding gradients. So during training, the gradient vector's magnitude can either become extremely large or extremely small during backpropagation. And this makes it difficult to update weights of earlier layers. That's a typo, which leads to training not converging. And this is most prominent when your activation function is something like sigmoid, right? Because your output is always going to be between 0 and 1. So you kind of multiply them all together, and eventually you get smaller and smaller weights, and you lead to either vanishing gradients or, in some other cases, exploding gradients. And we can kind of see a graph, right? So this happens during the backpropagation, right, time of training your neural network. So you can see, right, as the output layer, your weights are good, your gradient is good, but as you go backwards and backwards, it either like explodes upwards and your gradient is now huge all of a sudden, you can't really do anything, or it grows really, really small and you can't really do anything, right? So like I said, it's difficult to kind of train your neural network when you have gradients that are either really small or really large because it will not converge. And so this kind of plays into what we talked about before of parameters and also layers of neural networks learn at very different rates. And there's a lot of strategies to kind of mitigate these vanishing and exploding gradients. One of the most important thing is your weight initialization method. So kind of what happens with neural networks, right, when you're training them, is you actually randomize your weights usually when you first create it. And from your random weights is when you do the updates to it over time, and hopefully you do well. But how you initialize your weights can have a great impact on which minima you get stuck into or how you traverse the lost landscape. So it's very important. There's lots of different methods that you can have. Another idea is non-saturating activation functions. So like I said, sigmoid functions are considered as saturating activation functions, which means essentially as you go towards either infinity or negative infinity for the input, the output reaches either 0 or becomes, the gradient becomes either 0 or becomes 1, right? Essentially is what's happening there. So some other methods would be batch normalization, gradient clipping, and skip connections. You guys can, search that up. I'll leave that as an exercise for you guys. Oh, skipped it. All right. So let's see. I talked about saturating activation functions. Yeah, infinity. Yeah, so another main strategy that is used is to use activations like ReLU, which are non-saturating. And we talked about how tanh and sigmoid are saturating, right? So this is the reason why a lot of people use ReLU in their hidden layers, and they'll only use activation functions like tanh and sigmoid on the output layers, is because if you use tanh and sigmoid in the hidden layers, you'll usually run into this problem of vanishing and exploding gradients. And ReLU doesn't have this problem of vanishing and exploding gradients, but it does have another problem, which is called dying ReLUs. And so the idea here is that a neuron that uses ReLU as its activation function can die when all of the inputs that are passed into it are negative. So in this case, ReLU would always output 0, right? And so if it outputs 0, eventually what you find out happening is that it always kind of outputs 0 in all cases, and then that neuron is really not transmitting any information to the next layer because it's just always outputting 0 for some reason. There's a lot of different ways that people kind of do this or mitigate this issue, right? They have other ReLU variants, so similar to how you would use non-saturating activation functions, you can use other ReLU variants, right? Like leaky ReLU, I don't even know how to pronounce it, CellU, some other stuff. But most of the times, ReLU is actually effective, and ReLU won't really run into this issue. It's not the most common. I would say if you have extra time to train your model and it's not really time intensive, that you would want to use other safer variants, but it will be slower in training your model just because ReLU, obviously, if it's a negative value, just output 0, so there's not much to do there in terms of computation. But yeah. All right. So let's go through training a model as an example. And so a classic problem is the XOR problem, XOR, whatever, how you want to call it. The XOR function is a classic nonlinear function, and it's also an example that a lot of people use to demonstrate how neural networks can approximate nonlinear functions, right? Kind of the idea of the universal approximation theorem, right? So I kind of have some PyTorch code here just to kind of show as a demo, right? So there's two ways you can really initialize your model in PyTorch. You can create your custom class, right? And you kind of just inherit from the PyTorch main class, and then you can kind of define your forward paths, and you get a little bit more customization there. This one is the easier path, which is just you use the sequential module from PyTorch, and it's a lot easier for us to see, right? So we define our model as a neural network, right? We take in our first input layer, we take in two inputs, right? Because for XOR, XOR, we take in two inputs. We take the first input and the second input, and both of them are either true or false, right? Then we have our second hidden layer, we have our hidden layer. We only have one hidden layer, and it has two inputs too. So the layer one goes from two inputs, and it produces two outputs, right, for two neurons in the hidden layer, and also has an activation function when it passes it to the hidden layer. Then for the hidden layer to the output layer, we take in two inputs, and we produce one output, right? And then we have our output activation function, which is our sigmoid activation function. And you can kind of see a visualization of the XOR function on the right-hand side, right? You can see when given input 1 and given input 2, what will be your output, right? If you have 0, 0, you have false, false, so that leads to a false. If you have true and true, that also leads to a false in XOR, right? Because you want it to be exclusive OR. So you either have to have a true false or a false true in order to get a true, right? And so that's kind of what you see here, and there's no other inputs that you can give it, but we'll see later what our neural network does, right? So after this, we've defined our model. Let's set our hyperparameters, right? So we talked about how hyperparameter tuning is very important. There's a lot of stuff you can do, so we'll do some very basic stuff. First of all, we're gonna make sure that our loss function matches, right, our activation function at the end, right? And we're using sigmoid as our activation function at the output layer. So we're going to use binary cross entropy loss. It's essentially just a loss function that basically assumes that you have two values or two classes that you're trying to calculate the probability density functions for, right? So we're setting that to be our loss function, binary cross entropy, and it matches with our sigmoid activation layer. And then finally, we're choosing our optimizer. Like I said, we're going to be using stochastic gradient descent just because we don't really need anything fancy for this type of problem. And then we're going to set our learning rate to 1. And we're setting our learning rate to 1 here. This is very, very high for most neural networks. And the reason we're doing this is because technically there's only like 4 possible inputs you can give this neural network that makes sense. And so if you don't set the learning rate high in this instance, it will try and find a local minimum. And the local minimum is essentially predicting in between true and false every single time for every single value. So that's not what we want to happen. And also in PyTorch, you can print the model so you can see. And on the right-hand side, we have a graph of our model. It's very, very simple, right? We have 2 input neurons, like I said. We have one hidden layer with 2 neurons. And then we have an output layer with 1 neuron. And you can kind of see what PyTorch prints below it. It's a sequential model, linear layer, sigmoid activation function, and then the second linear layer. And then you have your final output layer, which uses sigmoid activation function again. All right. So let's train our model finally, right? So we basically just train our model. Here we're training for 10,000 epochs, right? Because like I said, technically there's only 4 valid inputs. So you can imagine our data set has 4 data points. There's not a lot to train on, so we're going to be training it for a lot of epochs, right, for our neural network to kind of understand what's going on. For every single epoch, we're going to be using our optimizer. We calculate the outputs using the model, right? We calculate the loss using the loss function that we've denoted, right? The criterion is our loss function, which is binary cross entropy loss. We then calculate the backward propagation, and then we use the optimizer to figure out what is the magnitude of our step we're taking in the gradient, or in the opposite direction of the gradient, right? And then on the right-hand side, you can see what our neural network actually kind of predicts for the values, right? So you can see at the bottom, very bottom of the graph, when it hits 1, 1, right, obviously it's predicting a 0. So it's predicting that you have a 1 and a 1, obviously you get a false. If you're predicting a 0 and a 0, you get a false, right? And then it shows kind of how it creates a nonlinear function. It kind of, as you hit either 0, 1 or 1, 0, you kind of have it go to true, right? And you can kind of see how the neural network is able to approximate the XOR function. Obviously, it doesn't make sense, the values in between 0 and 1, right? But we can see when we train our neural network, it doesn't really matter. It kind of maps to it anyways, and it figures out those ridges along the way, right? So that's what we kind of expect for this neural network here. Any questions? Nope. All right. Moving on. All right. So key takeaways from this lecture, right? We have a neural network, right? The ones we are talking about are feed-forward neural networks, so nothing fancy here. Each unit in a neural network is called a neuron, and it is the single unit of computation in the neural network. Each neuron belongs to a single layer, and every single layer in the neural network is fully connected to both its previous and the next layer ahead of it. A neural network approximates a target function that we want to map the test data, or the trained data, or the inputs to the outputs, right? And it approximates this target function through a weighted sum of nonlinear functions. And you can kind of see kind of an example of how this would work, right? We have f of x, which represents our function that we want to, our target function, and we can kind of represent it as a weighted sum of ReLU functions, right? Stuff like that. Plus a bias at the end, right? And then the thing for training neural networks is that there is a lot of hyperparameter tuning that is involved. There's optimizers, there's different things, stuff like that. And it makes it extremely difficult to make a neural network that performs well. But there are general tips and rules of thumbs that you guys can use. Stuff like the funnel architecture, batch size, number of neurons, and stuff like that we've talked about today is good. So that's good. The no free lunch theorem is the idea that essentially, unless you create the model and you test it, you don't have you can't say for sure whether or not that model will perform well or perform badly, because you don't know how the model performs on different problem sets, right? And then vanishing and exploding gradients is one of the biggest issues, right, in training neural networks. And this can be mitigated by the kind of strategies of hyperparameter tuning that we've talked about, how you initialize your weights, your optimizer, and different stuff like that is really important to dealing with these issues. So I believe that is the end of the lecture. So all you guys have signed in, I think. If you guys haven't, you can sign in again. But yeah, thank you very much for your time. I hope more people show up next time. I'm glad to have you guys all. I'm very glad. You 6, I'm very happy you guys came. But yeah, that concludes. If you guys have any questions or you want to discuss stuff with me, please come up. I think it's very useful. Anyways, yeah, I'll stop the stream now.